So I'll talk about an unsupervised framework for learning relationships from text. And I'll actually start with a few applications that I'll show you. Given the really short time, we'll see how much I'll manage to get into the framework. Probably it will be more about the applications. So this is the agenda. I'll give like very brief introduction to what is unsupervised relation learning. I'll show three applications. One is predicting FDA label changes of drugs based on the adverse drug reactions. Then I'll show the latest version of a system that can tell you where to invest. I'll show you actually something new from the past week, very interesting pattern language that can learn patterns that you can then apply for the trading. And finally, building company databases. In some of the text that we are using is actually extremely noisy. It comes from Alibaba. It was written in Chinese, translated to English, so you can definitely imagine that it's far from perfect. And if time will allow, I'll talk a little deeper about the unsupervised relation extraction framework. So this is actually the evolution of information extraction technology. At the bottom of the pyramid, we see rule-based information extraction. So this is really the 80s, 90s. On top of that, we have supervised information extraction, things like hidden Markov models, conditional random fields. You can combine the two lower levels into hybrid information extraction. And then you can start to use parsers to actually learn the rules automatically and use unsupervised learning in order to learn the different rules. So relation extraction in general is really to identify connections between entities in text. And in the traditional setting, you know what are the relationships that you actually want to learn. And there are two main approaches. One is really the knowledge engineering approach that, that you can use. One example is ClearForest, a company that I founded is now is part of Thomson Reuters, Open Calais, people that are familiar with that. And the other option is to use supervised learning. You actually give a lot of training data, and then you learn from the labeled examples. The problem is that both approaches take a lot of time. Definitely writing rules. At ClearForest, it took us really dozens of person years, to code all the rules, over 15,000 rules. So if you want to port it to a new domain, definitely it takes a lot of time. And also to come up with a lot of annotated data is very painful. So the approach that was pioneered by Oren Etzioni is open information extraction. The idea is that you don't know the relationships. The system learns the relationships automatically from the corpus. So this is basically what we're using. I'll start to talk about the applications. So one of the main problems is that you can see the fourth leading cause for death is due to ADRs of drugs. And the problem is that the ADRs that the companies find in the clinical trials are only a partial list, and many of them are actually discovered years after the drug was released into the market. The FDA usually is very late to changing the label. You know, this pamphlet that you get, if you actually read it, usually you'll get a heart attack just from reading how many bad things can happen to you if you use the drug. So probably most of the people don't even read it. But one of the problems is that the FDA really doesn't have a lot of information to do the changes way before actually it killed already a few people. So the main idea is to use a text mining methodology that will be able to detect those ADRs way before the FDA is doing it. So we are using the unsupervised relation extraction framework, basically to learn all those relationships between drugs and symptoms from user forums. I'll show the main things that we need to do. There are actually 4 steps that we're taking. We have the pre-processing, where we take all the messages from the forums. We learn all the different relationships by using the unsupervised relation extraction, perform the extraction on the text. The learning usually will be done only on a small portion of the full collection of messages, because the learning definitely is much slower than the actual extraction. So we do sampling. We take, let's say, 1% of the messages. We perform the learning on that. And then we perform the extraction using the rules on the rest of the messages. And finally, we have post-processing that I'll show you. So in the pre-processing, basically, it's a lot of cleaning, removing duplications, parsing, etc. The relation acquisition is really to learn all those relationships between drugs, symptoms, people, and we talked about the extraction. The post-processing is actually interesting because in many cases, we have different relationships that we can combine together to a bigger relation. So you can see, for instance, in the sentence, I took Lipitor. So that's a connection between a person and a drug. And then later, there is a connection to the ADRs, and then you want to connect between the drug and the ADR. So we do it at the post-processing level. Then you can actually get a map that will show you all possible relationships. So this is really just a summary map. What I want to show very quickly, and I won't get into all the different details, I'll just show the 2 examples in order to show some more applications, is first seeing that statins can cause cognitive impairment, memory loss, and stuff like that. And we found it around 7 years before the FDA actually announced it. So what you can see here is really the summary, and you can see that the cognitive impairment in statins definitely, compared to all the other types, was much, much higher, 97, you can see, compared to 1, 4, 2. So definitely much more evident, the connection between the statins and the cognitive impairment. This is actually all the analysis of all the statistical chi-square and stuff like that. We used mainly the lift value that shows the connection between the association between the drug and the ADR. And then we made sure that the chi-square of the lift is actually above, it actually is validated statistically. Again, due to lack of time, I won't go to all the details. The other example is using Wellbutrin to cause, it actually causes agitation. And again, very similar analysis, and you can see that there is definitely a very strong connection to Wellbutrin, much more than the others. Again, the same type of statistical analysis. So in most of the cases, we saw that any label change that was done on the FDA, just by the analysis of the user forums, we can find it around 7 years before the FDA issued that. Here you can see the accuracy that we got. The precision you can see is around the high 80s, low 90s, and the recall was around 70%. And remember that everything is unsupervised. We didn't write a single rule, so that's pretty nice. Okay, the next application is actually how to use sentiment for stocks. So one of the main problems is if you use very simplistic sentiment analysis, you'll just look at the words, you'll see if there are positive words or negative words. and then you'll say that this sentence is actually positive about Toyota. But the main thing is really the recall event. So you need to identify that there is a recall event. A recall event definitely is a disaster for any car company. And then you want to issue, in this case, a negative sentiment. And if people remember, the stock actually went down about 30% after that recall. This is the architecture of the system. We actually collect from many different websites, actually hundreds of websites, that we collect information using the crawlers, clean all the HTML, identify what is the relevant text to each entity. In this case, the entities are the tickers of the stocks. Then we perform hybrid sentiment analysis. I'll talk about it in a second. We do the scoring of the sentiment for a single document. We use the full set of documents with decaying effect, so older documents will have lower weight. And finally, we have a score for the whole set of documents for the specific stock between -1 and 1. So the hybrid sentiment analysis is actually using both dictionaries, patterns, and events. And of course, the most relevant to the unsupervised is the events. We identify over 70 different types of business events that are related to the stocks. Anything that you may think about related to the board, the products, the dividends, the earnings, litigation, you name it. So we find all those different events, and using the three models together, we can actually get the score. This is about the dictionary, which again, we use machine learning to basically perfect the dictionary for financial applications. You can see some of the examples for the events. And now you can see what we can do with it. So basically here, you can see Broadcom, for instance. You can see here three graphs. The blue graph is the price of the stock. The green graph is the positive sentiment. And the red graph is the negative sentiment. We are interested usually in a jump. Let's say we're talking about the long side. We're interested in a jump in the positive sentiment, and actually the stock either didn't move or went down. And then, in that case, we'll actually go long. And as you'll see, and we validated using the pattern language, in most of the cases, actually, it does go up after that. Okay? You can see a very similar example for Juniper. You can see a really huge jump in the sentiment here. The stock almost didn't move, and then the big jump came later. And I'll show you the validation. Here I'm giving you anecdotes, but we did the full backtesting to see if it really scales over every instance. And you'll see the results in a second. This is for negative sentiment for SanDisk. I don't know if people followed. Recently, they really crashed from around $100 to around 60. Jarmin, very similar. So basically what we did, of course, you cannot read it, but what we said is let's define actually a pattern language when you can define really very general patterns that are related to sentiment, to events, and to the stock movement. And then we can actually even learn the patterns, but then executing the patterns will be very fast. So in this case, you can see an example for IBM. Usually the people that did hold IBM, the IBM stock in the past year were not too happy. But at least here, we actually saw that there was a jump. So the system basically will show you every time that there is a positive alert. If it succeeded, it will say predicted. If it failed, it will write failed. So in this case, you can see that out of four, we actually managed to be correct in 3. In one of them, we failed. And very similar to Cigna, which is a big insurers in healthcare. You can see again, positive alert, and again, it was predicted. So this is the full system. In this case, you can see we sorted how the pattern succeeded. So you can see the top one actually managed to give us a 89% return just by this pattern. This is actually around 15 trading days. So it's not bad. 15 trading days to get that. And you can see in most of the cases, you actually get pretty good returns. Here you can see the statistics that actually changed a lot in the past week. So you can see, for instance, for the positive alerts, we got 58% success rate. But the average performance, even if we include all the failed alerts, was 1.26% per alert. Now, just for comparison, and this is, I'm talking about for 15 trading days, the average return for the S&P 500 for this time period was around 0.6% per month. So this is definitely much better than the S&P. You can see that in negative, in this case, it was still bad. Since then, we actually managed to improve that as well. The last application that I want to talk about is how to create company databases. So the input would be either company websites, company directories, or e-commerce sites such as Alibaba. One of the main problems that we faced is that there is a big difference between the quality of the text. So if the text comes from a professional website of an American company, no problem, you can use parsers, you'll get excellent results. If you use text that you got from Alibaba, it's pretty horrible text, so the same method won't work as well. We wanted actually to have one method that will be able to work across the board. Doesn't matter if the text is good or bad, we don't have to worry about it. I mean, there are other methods that we could try, but we wanted to have one method that will fit all. So the main thing is we learned actually extraction rules using the unsupervised learning framework, and we found the probabilities. So in each case, it might be that a few of the patterns fired, but we will take only those that had the higher probability for that particular instance. And for that, we actually got pretty good accuracies. What we used, after we did the first run of the system, we gave it to an analyst that went over. If you see green, it means that they said that the output of the system was correct. Red, the output of the system was incorrect. And then we actually trained the system again based on the feedback. And you can see finally this is the precision and recall that we managed to get for identifying the products and services of the company. Location, so some people will think, okay, what's the big deal? You'll just find the geographic location. The thing is, you don't care about where the company is based. You care where the company is catering to. So you want to know which geographical regions the company is trying to serve, and I don't care actually where the company is located. So that was a little trickier than it may seem. So in the maybe 2 minutes that I have left, I'll show a little bit, try to pick some of the most interesting slides. So let me first go over the flow, how the unsupervised learning is happening. Basically what we do is we take the training data, which is just unannotated, unlabeled text that we got, and we perform full parsing. We actually have two versions of the system. One version is based on a proprietary HPSG parser, and another one is based on an open source Stanford dependency parser. We definitely saw a difference. The proprietary parser did perform better because it was information extraction focused. So we parse the whole set of sentences, and then we keep only the patterns that we have at least 2 sentences to support. So all the singletons, basically we delete because usually they would be noise, and we keep all those patterns, and then we can apply the patterns to extract things out of the rest. Here you can see different type of the patterns very quickly just to see how patterns look like. So this is verb patterns, noun patterns, in this case around acquisition and mergers. Be pattern is a very special verb. You can see the accuracies that we managed to get in this case, precision, definitely pretty high precision considering that everything was done automatically with not even a single rule written by hand. So that's it, exactly on time.
Thank you very much.
Yes? Okay. So you know, in information extraction, there is a very big debate for dozens of years whether to do shallow parsing or full parsing. And traditionally, it was believed that shallow parsing works better. But recently, with the advancement in parsing, academics and startups are starting to use full parser. The parser is probabilistic, so anyway, we're using a probabilistic context-free grammar. So we get the probabilities for each of the parsers, so you can utilize that. We take the whole sentence and parse it. We don't try to cut it and parse different parts. But you know, maybe cutting it will work better. Okay.
Yeah, the stock example, the additional gain from sentiment analysis versus the signal itself. I mean, the question is, was the information already in the signal, or is there additional information? For example, if something is dropping, there's negative sentiment in the market anyway.
Correct.
Yeah.
So if there is a negative sentiment and the stock dropped, we do nothing. This is why we have this condition that we must see that actually the market did not react to it yet. If the market reacted, too late. So if there is a very positive news and the stock jumped, nothing we can do. We lost it. We're late to the game. So we're looking only for the cases where still the market is not efficient, did not absorb the news, whatever, and we're trying to use exactly those hours or days sometimes to take advantage of that.
Hello. I noticed that in many cases there seemed to be a rise in the positive sentiment and in the negative sentiment at the same time. And I was wondering, is that a general phenomenon, and how do you interpret it? Because that could be quite confusing to a classifier.
Right. First, you're right. In many cases, there is a simultaneous rise in the positive and negative sentiment. It might be because, like, somebody at Seeking Alpha will say, here are the positive, here are why I am long the stock, but there are also some weak points. So the main difference is the ratio. So is it much higher, the positive, or if it's about the same, then it's neutral. If the positive is much higher than the negative, then I take it as a positive thing. But in the pattern language, for instance, you can actually, inside the query, specify what's the ratio, how many negatives and positives, so you can really play with it. Now, the next thing is actually to learn from the market and try to identify what are the best patterns automatically, and this is what we're doing now.
So it's not just a positive predictive value, you actually have to combine.
Yes. There are a lot of features that actually we can get. The fact that we get the events is extremely powerful. I can tell you that some companies do event studies You know, even PhDs or professors at the business school in the finance department, sometimes they do event studies for months. We can now do a full event study in 90 seconds. So that's a huge difference in terms of the research power that you get out of it.
Okay, let's thank you, Ben-Gurion.